Okay, so now my challenge is to live up to that introduction. Not a chance. I'll do what I'm going to do, and I'll have a good time, and thank you so much, Gary. I told Gary before the talk I'm glad he didn't talk to certain of my friends at UNC, or the introduction might have been entirely different. In any case, at some point I'll get a chance to introduce Gary, and I'll hope to be half as charming and effective in my introduction, and it will be quite a good introduction in that case. Thank you. So welcome. Nice to have you guys here. It's really nice to be able to give this talk. This is a fun talk. Gary gave it all sorts of accolades, and this is fundamentally at its very base a fun talk. It's a talk I've been preparing to give for about 35 or 40 years. In a very real sense, all that I've been doing for a very long time has been getting me ready to give this talk. And I'll tell some stories associated with what got me here, with what got us here. The biggest challenge of all in developing this was deciding what in the world I should title it. You've seen the title. It was actually a little mixed up in the circulation. This is the actual title of the talk that went out and circulated through Peabody: Galileo and Significance Testing versus Newton and Mathematical Modeling, Revolution Backward and Forward. That's a little obscure, right? Except you know who a couple of those folks are. There's another title that I almost used instead, and there it is: Statistical Models as Constrained Language Structure, Poetry, Art, Math, and Theory Testing. And I'm still not at all sure which one I should use. So you guys tell me, who likes the first one? Who likes the second one? No, it's almost tied. I think there was a slight preference. So this is my title. This is my title. I'll be talking about Galileo and Newton and various things that pass through those guys. And I would like to tell you a little bit about the talk. This talk is a presentation about mathematical and statistical models. Well, you knew that. Those of you who know that I came here to work with the Quantitative Methods program and just listened to Gary's introduction, got a sense of the fact that I need to give a talk about mathematical and statistical modeling. That's what I do. That's how I think. But it is also a presentation about language structures. That's a little bit surprising, all in the same talk. And in fact, it's also a presentation about art, about a certain kind of art, about symmetric art. Those seem rather detached, but I'll make it my challenge and my goal to try and bring those together as I give the talk. So really my overall goals today are to show how mathematical and statistical models are really just constrained versions of language structures and artistic structures. I'll discuss the transition within behavioral science research that has been going on for quite some time now in fascinating ways, from an hypothesis testing paradigm to a statistical modeling paradigm. And in the course of this, we have a very interesting way that our methodology has softened in, I think, appropriate ways, although that's arguable, and some of the tension that we'll talk about comes from that. And ultimately, I want to cast this transition into a broader perspective that includes some comments about the history of science and Galileo and Newton and a few other luminaries. Roald Hoffmann is a chemist who won a Nobel Prize a few years ago and wrote an article in American Scientist, not about chemistry, thank goodness. I couldn't have read his article about chemistry and appreciated it. But this one I read with great interest because it was an article about theory building titled "Why Buy That Theory?" And I've been using this quote in most of my talks ever since then, not just this one, but others. He said, "Many theories or models are popular because they tell a rollicking good story, one that is sage in capturing how the world works." And so today, in this spirit, I hope to tell some rollicking good stories and to talk about storytelling as well. So not only will I tell the stories, but I think it's important as a methodologist that we back out and look in at how we tell the stories. And so that'll be part of the message. Some main players, I stand on the shoulder of giants. There's some big names on here, not just Galileo and Newton, but a few other folks. I'm not going to read all these names, but as you glance through those, anyone who has been connected with the field of statistics or psychology or social science broadly defined, or hard science, general science broadly defined, will recognize names on this list that you'll appreciate and recognize. Part 1. Mathematical and statistical models as constrained versions of language structure and artistic structure. And so Thomas Stearns Eliot wrote, "Let us go then, you and I, when the evening is spread out against the sky, like a patient etherized upon a table. Let us go through certain half-deserted streets, the muttering retreats, and the ladies come and go, talking of Michelangelo. No, I am not Prince Hamlet, nor is meant to be. Am an attendant lord, one that will do to swell a progress, start a scene or two. To swell a progress, advise the prince, no doubt, an easy tool. Deferential, glad to be of use, politic, cautious and meticulous, full of high sentence, but a bit obtuse, at times indeed almost ridiculous, almost at times the fool. I grow old, I wear the bottoms of my trousers rolled. Shall I part my hair behind? Do I dare to eat a peach? I shall wear white flannel trousers and walk upon the beach. I have heard the mermaids singing, each to each." And this is, of course, just a small part of the love song of J. Alfred Prufrock. And it doesn't show up in this talk in obvious ways, but an English critic could present that and talk about that for a long time, and would discuss how ironic it is that a 23-year-old poet, as T.S. Eliot was when he wrote this, could write with such evocative nuance about the process of growing old. How did he know about rolling his trousers and about parting his hair behind? And yet somehow he did. So let's think about this as a constrained language structure. That's indeed, of course, what poetry is. It has certain constraints that are obvious to us. We learn those when we're children. First of all, at its most basic level, a lot, not all, but a lot of poems have to rhyme. And among the most famous of all the rhymes in the English language are some of T.S. Eliot's couplets, like, for example, "In the room the women come and go," talking of Michelangelo. That's satisfying the constraint and also saying something that's neat. Suppose instead he'd said, "So the women came to the museum and wandered through and looked at some paintings that Michelangelo produced." Would we be repeating that today? Probably not. It's that constraint and the fact that he achieved it in a very nice way that makes it remarkable. But there are other constraints in poetry as well. I've pointed out some of the rhymes that are in here. But in addition, up here you see that there are parts of the poem that build and progress and refer to one another. If you look deeply, you'll see a couple of references in here that are fairly Shakespearean. Here's Prince Hamlet and the Fool, and if I were a professional English critic, I'd probably have all sorts of things to say about that. I don't. I just point out that another of the constrained language features of poetry is that it's supposed to build and grow and make you elaborate almost by inference as you read the poetry. Well, my father bought a Civic a couple of years ago, and I helped him buy that Civic. And I noticed as I was doing that, I bought a Honda for myself 15 or 20 years ago. Noticed while I was in the Honda dealer that they had changed the Civic logo to achieve a certain very neat lexicographic goal that is actually a visual palindrome. And so if you look carefully, you'll see that they changed the C at the end around. And so this is now symmetric about that axis. And I don't have any idea what smart marketing expert was hired that got paid a whole lot of money to come up with this innovation. But one person really liked it. I sat and looked at this while my father was haggling with the salesperson and liked the fact that there's a palindrome, at least at the visual level, built into this, and remembered it and brought it into this talk. Constrained language structure, constrained in a different way than the poems, constrained to be symmetric. Whoops. So we can solve this, but let's see. Well, let's see. I'll do this by hand. There we go. Okay. So even before I got there. So Scott Kim produces beautiful, constrained artistic systems. Scott Kim is an artist that can take language structures, letters in particular, words, and use the ambiguity built into those language structures and produce beautiful symmetric renderings. And so this, of course, says Merry Christmas. You never thought otherwise. You immediately recognize that. But study that for a second and you'll see that this M is also this RRY in reverse. And you'll see that not only is this a gorgeous rendering of the word Merry Christmas, but There's other things built into that. It looks like a sleigh, perhaps, or maybe those are mountains. I'm not quite sure which, but certainly makes me think of Christmas and winter and so on. And so this was one of his Christmas cards back in, whatever that says, 1979, I think. And I saw that and I admired that so much that a few years later, I tried to produce my own Kim art. And you'll see that I'm not nearly the artist that Scott Kim was. But indeed, I did achieve a little bit of the same goal. We sent this out to many dozens of our friends as our Christmas card that year. A very few of them, maybe only 3 or 4, noticed the Scott Kim art here. This is our name, Rodgers, rendered in such a way that it is symmetric up and down. In other words, you can flip it over and it's still Rodgers. And so my little nod in the direction of appreciating symmetric art. And it was fun to do, and sure enough, I produced a language structure that is constrained in a certain way. And when you Google haiku, the first one that comes up, the first several that come up, apparently Bashu Matsuo is quite a famous haiku producer because the first several Google responses that come up are haikus that he produced, a Japanese poet. This is an especially evocative one, an old silent pond. A frog jumps into the pond, splash, silence again. Now, I like that because that evokes an image. I read that and I can see, hear the frog. I think that's very beautiful. But of course it has the constraints of a haiku, 5, then 7, then 5 syllables in each line. And even more apropos haiku showed up on the blackboard across the hall here during a faculty meeting a year or so ago, and I asked around, and it turned out that David Cole, the psychology department's chair at that time, had a son who likes to write, and he produced a haiku that goes like this: little p-value, how can something so tiny be significant? That's really deep. That's neat. I have not met Bryant Cole, although I emailed with him and told him how much I liked that and asked if I could use it in my talk. And he said sure, and we're all the better for it. And so here is Richard Lederer, who writes a column titled Looking at Language. And in that column one day he published simply a mathematical statement that is true. Not much there, right? It is true that on the left-hand side it adds up to 81. And on the right-hand side it adds up to 81, and so therefore it is in fact justifiable that we have an equal sign there. And that's the mathematical constraint, but there are other constraints here that are actually elegant that you may not have noticed. And so it turns out that, in fact, a dozen, a gross, and a score, plus 3 times the square root of 4, divided by 7 plus 5 times 11 is 9 squared and not a thing more. And so this is not only a true and correct mathematical statement, it is a limerick that satisfies the constraints of limericks, that they have a certain rhyme scheme and meter and so on. And so Richard Lederer didn't invent this. He didn't know where he got it, and I've always wondered. But imagine if the poet here had produced this and done the arithmetic and got to the end, and on the left-hand side it added up to 80. He would have said, well, darn it, I satisfied the constraints of limerick and meter and poetry, but I didn't satisfy the mathematical constraints. But indeed, he or she did both, and that's very neat. And so we have another constrained language system that is constrained mathematically and also linguistically. And so that leads me to a discussion of a line of research that I began with David Rowe, my colleague from the University of Oklahoma and then the University of Arizona for many years, that we began back in the 1980s. And this is a line of research that we titled Epidemic Models of the Onset of Social Activities. I had a mentor in graduate school at UNC, Forrest Young, who told me that it didn't matter how good your work was as long as the acronym was pronounceable. And so this is called EMOSA modeling. EMOSA even sounds a little bit like ANOVA, and so psychologists like it because it has that nice little ring to it. EMOSA models are epidemic models, social contagion models, that explain the spread not of disease or biological substrate, but rather of ideas, a joke, or innovations, a new laundry detergent. And we think of these as spreading through a social network, through a contagious type of process. We've written a number of EMOSA models in the past 25 or 30 years, and we've studied adolescent sexual behavior, we've studied smoking and drinking and delinquency and religious transitions, all from the standpoint that changes or shifts, or especially the onset, the O up there, is somehow reflective and responsive to social contagion. And I'll talk a bit more about these. These are models that I can talk about without embarrassment because they're our models, we've developed them, and so the strengths and weaknesses built into those, I don't have to deeply apologize in relationship to anybody else. I can just talk about them. There's an EMOSA sexuality model. And aren't you glad you came? Okay, so we're done. You guys good? Or maybe not. That's a set of equations, and those equations have all sorts of, pardon me for a second, poetry built into them. But hang on to that for a few moments and I'll come back to it. This is a set of EMOSA equations that define an EMOSA sexuality model that talks about transitions between levels of sexual intimacy among adolescents in an intact adolescent community. It's hard to interpret that unless you are David Rowe or myself and know exactly what it says. And so let me untangle that a bit. From one of our first EMOSA publications in 1989, this equation says that the proportion of adolescents who have ever engaged in some behavior, in this case it's ever engaged in sexual intercourse, it could be smoking, it could be playing in the school band, it applies equally, is a process that can be broken down into three components. The first component is the carryover from last year. So if you've ever smoked or drunk alcohol or engaged in sexual intercourse last year, of course, logically, you still have ever done that this year. So the first one is not all that interesting. That's the carryover component. This part is what we call the epidemic component. And so of all of those last year who had never engaged in the behavior, that's 1 minus p sub t, who came in contact in a social setting with someone who had engaged in the behavior, in this case, the potential opposite sex partner who had ever had sexual intercourse, with some transition probability t, this person transitions into the behavior that we're studying and becomes part of the proportion who have engaged in the behavior by this year. The third part is the non-epidemic part where, let's say in this case we're talking about a virgin and a virgin contact, opposite sex contact, that with some different transition probability could result in a transition into non-virginity and adding to the p-value. So that's what all these equations say about some behavior or other, and I'll talk about quite a few behaviors as we pass through this conversation. And I have to say there's a lot easier way to represent this than through those equations. It doesn't take very long to look at those pictures, and it is exactly the case that these are isomorphic expressions. These equations say the same thing that these pictures do. So what these pictures say is that among an intact community of age 12-year-old young adolescents, some of whom are females and some of whom are males, some of whom are virgins and some of whom are non-virgins, with these different transition probabilities represented in K, TF, and TM, the age 12 community interacts with one another and becomes an age 13 community in which there are a few new adolescents who have ever performed the relevant behavior. Okay? So this is the social contagion model. And this cycles on and on and on, and eventually by age 18, according to empirical studies, a bit more than half of the adolescents in the U.S. report ever having engaged in sexual intercourse. And so that's what this model is trying to capture and account for. Of course, we use variables, we use measures, we use data to which we fit the mathematical models to estimate the parameters. So there really are three pieces of the structure here that are relevant. One is the data structure that says what the proportion of male and female virgins to non-virgins are at a given point in time. The second part is the mathematical structure that you see right there. And the third part comes from blending those two together and asking the methodological statistical procedure to estimate parameters that are optimal in some least squares or maximum likelihood sense that tell us things about the system. And in this case, there are three parameters, K, TF, and TM. And what published our first article, what made it interesting to the reviewers and editor to publish was that the K and TF and TM were very interpretable parameters. K was close to 0, barely larger than 0, suggesting that virgin pairings of adolescents don't very often result in new non-virgins. TF and TM were exactly what you'd expect them to be if you watch movies, or if you read books, or if you have teenage children. They work just like you think they would. It's much easier for a adolescent female who has ever had intercourse to convert, if you'll pardon my phraseology, to convert virgin male to non-virginity than the reverse, and so on. So that was the beginning of our work with adolescent sexuality in the context of EMOSA modeling, and I'm going to move on and show you some new things in a couple of seconds, but I want to back up a little bit and review where we are now. We're talking about mathematical constraints in the context of artistic and language constraints. And I want to quickly note that those of you who are sophisticated and have done a whole lot of work in areas like structural equation modeling, multidimensional scaling, log linear modeling, some of the sophisticated modeling approaches, will recognize that we have counterparts among correlations, which are themselves defined to be symmetric by definition, among Euclidean distances that we use in scaling exercises, which are themselves defined to be symmetric. That's not tough. We live in a Euclidean world. The distance from my nose to every other nose in this room is a symmetric process. Same distance from mine to yours as yours to mine, and so on and so on. So we are aware that there are symmetry constraints built into our mathematical models, and we can capitalize on those. But let me push this a little bit further. And note that when we're telling a rollicking good story in poetry or children's stories or novels, we can also extend this kind of rollicking good story into the kinds of mathematical models and EMOSA models that I've started talking about. And so here we are back to this picture again. We've already deconstructed this, but let me push it a little bit further and note that there is a kind of a rhyme scheme built into these. I've expanded this a little bit, and if you look carefully, you'll see that there's T sub M1 and T sub M2 and T sub M3 and T sub M4. Those are not literal language constraints in which they actually rhyme, but that's a little bit like a rhyme scheme. And in fact, it turns out that these occur in pairs. These equations are, that's the male equation and that's the female equation, and there are 4 of those. So these are a little bit like 4 couplets. And furthermore, parts of each equation talk to the equation 2 down from it, and so there are further constraints, a little bit like Prufrock, where the Shakespearean flow could be observed throughout his paragraph. Not quite the same. It's not a perfect analogy, but I think I can argue that there's a little bit of something like poetry built into these mathematical models. And I have to admit, this is not for me to take ownership of. This is in no sense my first idea or only my idea. Paul Meehl, quite some time ago, was interested in the concept of model verisimilitude. The idea that models have beauty and truth-likeness as well as just a bunch of mathematical symbols. David Thyssen from University of North Carolina was the president of the Psychometric Society in 2001, and during his presidential address he quoted Picasso. He quoted Picasso to say that art is a lie that enables us to realize the truth, which reminds us of a famous quote by George E.P. Box that says that models don't have to be true. In fact, all models are false, but models don't have to be true, they just have to be useful. And so all of these folks are coming together with the same basic idea. However, notice that statistical and mathematical models, if we really crawl inside those, have a little bit different features than language structures. James Joyce, goodness knows, could write 1,000 pages about a single day. If you tried to do that with a mathematical model, it just wouldn't work, because part of the goal of a mathematical model is not only to build it to fit the data, but also to achieve a certain other criterion, which is called parsimony. We want it to be simple. And so a good poem or a good novel may or may not be simple and straightforward. Some of them certainly are not. But good mathematical models in some context need to be a little bit simpler than their competitors that are equally good at fitting the data. Or another way to say that is, if I want to improve my model a little bit, I'll improve it by making it fit the data better, but I better do that in recognition of the fact that my more complex model comes at a cost. More on that in a few moments. Part 2. Part 2 actually is a slightly shortened version of my presidential address to the Society of Multivariate Experimental Psychology, where I first got started on this line of writing. This is where I first started thinking these thoughts. That's not right. I was thinking these thoughts for a long time. The first time I'd actually codified them and written them down on paper. And so the second part is titled The Epistemology of Mathematical Modeling, a Quiet Methodological Revolution, or sometimes, because it has quite a strong pedagogical orientation, I refer to it as putting the modeling heart before the methodological course. And so, maybe I'll just walk over here and that'll trick it. So I've already said this, and by the way, this was eventually published. I presented it in 2005 and spent the next 5 years refining it according to the expectations of many, many reviewers who beat it into submission and helped me make it better. Most of them made me change it in positive ways. I thought a few of them forced me to take a step or two back. That's the way it goes in our profession. So there are models all over. Models abound. There are airplane models. I built those when I was a kid. And there are runway models, and there are Model Ts, and there are role models. And the word model actually can be united across these in certain interesting ways, but ultimately we want to get around to the idea of a mathematical model. And so Neiman and Estes a long time ago said that a mathematical model is a set of assumptions together with implications drawn from them by mathematical reasoning. Bob Bjork, also a long time ago, listed the advantages of a mathematical model compared to a verbal model. There are lots of verbal models in behavioral science. If we can make them mathematical, then they have certain advantages, and among those are that they are falsifiable, they have theoretical precision, the assumptions can be formally defined and more carefully evaluated, they improve our data analysis potential, and they make practical applications a little bit more straightforward. Whoops, wasn't quite supposed to. And so here's what I want to go. So with all of this background, I want to talk about an historical period of time, a historical moment in the development of methodology that is very Fisherian, because Fisher got it started back in the 1920s. And Gary's reading from a book that I have read and that I like very much because it talks about one of my intellectual heroes. He's not a personal hero. He was sort of a scumbag, comes to mind. He wasn't a wonderful human being. He wasn't a good father. He wasn't a good husband. He was not a great friend. But what a brilliant, brilliant, smart man Sir Ronald Fisher was. Besides being a statistician, he also invented the field of quantitative genetics as a hobby on the side. Besides doing those two things, he also was the one who developed the blood typology. So I'm O pos, and my daughter is O negative, and we know that because Sir Ronald Fisher is the one that came up with that cluster structure. And so he was quite a remarkable scientist, but he's best known, perhaps in some settings, for his statistical wherewithal. He invented the field of null hypothesis significance testing, the paradigm, the approach, the epistemological method that we call NHST came from Fisher. By the way, as we'll see, he wasn't all that enamored with it. He thought he could do better. But he certainly invented it, and he sold it. And it's been so successful that still today in undergraduate stat, which I'm teaching right this very minute, building right across the quad here this morning, I talked about NHST issues. We're all teaching NHST concepts today pretty much the way Fisher and some of his early colleagues developed them. So in the late 1990s, and you have to listen carefully, the field of psychology, of psychometrics, of quantitative psychology, put NHST on trial. And during this period of time, it looked like NHST might end not with a whimper, but with a, shoot, let me try it again. Yeah, maybe this will work now. Ended with a whimper, but rather, did not end with a whimper, but rather with a, okay, not much of a bang, but anyway, you get the point. So there were people within my field, some close friends of mine, in fact, who called for NHST to be outlawed, eliminated, legislated out of existence. This is not a passive type of effort. It's not an effort where Frank Schmidt stood up and said, you know, if we let this flounder long enough, NHST will just sort of die its own natural death. Not at all. He said, we've got to kill it, and while it's still quivering, we've got to step on it and stomp on it and make sure it goes away. NHST, hypothesis testing, significance testing, t-tests, f-tests, chi-square tests, and so on, are often taught from a jurisprudence standpoint. The jurisprudence approach says that we put the null hypothesis on trial. We assume its innocence until proven guilty. In other words, we assume the null hypothesis until the burden of doubt causes us to reject it. The prosecutor, the researcher, is entitled to develop a case. There's a detective, the data analyst, is helping to amass the evidence. The jury is the skeptical scientific community who, I promise, anyone who's ever submitted a paper, especially your first couple, can attest to the fact that the scientific community can be very skeptical about your work. And so ultimately, however, this very legal type of process was itself put on trial. It's really interesting that NHST, a legalistic type of procedure, was being put on trial by the field of psychology, and in fact the APA, the American Psych Association, formed a task force of its very best methodologists, 8 or 10 well-known, very famous people, with Jack Cohen was the chair of that committee. Bob Abelson was on it. Mark Applebaum, who used to be a Vanderbilt faculty member, was on that. Susan Embretson was on it. Many, many luminaries from quantitative methods were on this jury that was empowered to put NHST on trial and decide whether to make it go away forever, to outlaw it from journals. So what Schmidt said, what Frank Schmidt said in his writing was, we must abandon the statistical significance test. Jack Cohen published a famous article titled, "The World is Round," in parentheses, p less than 0.05. And that was a critique and a very much a criticism of NHST. So this APA task force that Lee Wilkinson ultimately ended up chairing, Jack Cohen ended up passing away in the course of this. So Lee Wilkinson is the one who wrote the final product, and people in my classes routinely read the final product, which was published in American Psychologist around 2001. And so let me talk a little bit about the background of this NHST paradigm and see if we can make sense out of how we got to that point. How did we get to this big explosion where the field of psychology was trying to consider whether to simply outlaw an intellectual procedure? It's just a procedure, folks. A t-test is just something we do. And Frank Schmidt was saying, no, we can't do it anymore. That's a pretty strong statement. So how did we get there? Well, here's Fisher on the left-hand side. And back in his heyday, he fought with everybody. He was a contentious guy. He was sure he was right. He often was in a strict scientific or mathematical sense. He was a brilliant mathematician. His biggest critic from early on was the very famous British statistician Karl Pearson, who he fought with when he was about 20 years old. Pearson referred to Fisher as tilting at windmills. In other words, he was the windmill and Fisher was trying to duke it out with the windmill. Turned out Fisher was right in his criticism of Pearson, and they never liked each other after that. That's a mild way of saying it. Pearson's son, Egon Pearson, and his colleague Jerzy Neyman continued the running antipathy, And so Fisher and Neyman and Pearson fought it out in the pages of journals for 20 or 30 years over exactly how to do NHST. Fisher didn't believe in the alternative hypothesis or in power. Neyman and Pearson didn't believe that you could draw any strong conclusions without doing a power analysis. Sounds like your dissertation committee, doesn't it? Without doing a power analysis, without doing all sorts of things about a null and alternative hypothesis. So they really did fight it out in the pages of journals, and what's ironic is that now what's in our standard statistical lore is exactly the combination of these two folks. It's half Fisherian, it's half Neyman-Pearsonian. And so Christensen said Fisher used the distribution of the null model and simply examined whether the data themselves looked weird or not. On the other hand, he said Neyman-Pearson testing is designed to optimally detect some alternative hypothesis, which Fisher decried and would not admit to the legitimacy. And ultimately, Christensen said MP testing and Fisherian testing are not comparable procedures. Gigerenzer goes even further. He says our current practice is an incoherent mismatch. Wow. So that's what I'm teaching. Okay. An incoherent mismatch of some of Fisher's ideas on the one hand, some of the ideas of Neyman and E.S. Pearson on the other hand. He said this back in 1993. So just to remind you, everyone in the room knows what NHST is if you've had any background in statistics. The mantras say you shall not capitalize on chance. The null and alternatives must be stated explicitly, and they must be stated before we see the data. And ultimately, the power of a statistical test to reject the null can only be stated in relationship to some specified alternative. That sounds like it comes straight out of the pages of any one of 100 different statistical texts. And of course, there have always been critics, including Fisher himself. The quote from Fisher is, "The analysis of variance, which gave rise to NHST," he said, "is only a convenient way of arranging the arithmetic." That's how he didn't say it's a paradigm. He didn't say it's an epistemological system. He didn't say we need an acronym, NHST, to validate it. He just said it's a convenient way to arrange the arithmetic. So Fisher was not all that impressed. He actually invented maximum likelihood estimation, and he really liked that. He thought that's what we should be doing. But that didn't stick. What stuck was NHST. Besides Fisher himself, and by the way, that's what the first paper looked like, and table 11 there is his first ANOVA table, built inside an article on crop yield and, how can I say this gracefully, crop yield and levels of manure spread over the crop. So you can do with that whatever you want to do with that, but his first paper is titled Studies in Crop Variation, an Examination of the Yield of Dressed Grain from the Broad Bulk. And so there's the first ANOVA table. It was just buried, table 11, inside an article. He wasn't trying to invent a new statistical paradigm or epistemological system, but indeed he did. The only even close to comparable paradigm shift that has occurred during the 20th century was when John Tukey in 1977 published a book that said we need to jump out of the NHST paradigm a little bit. He didn't hate it. He wasn't a big critic. He was a little bit of a critic. But he wanted to expand it. And in fact, among all the critics, my mentor in graduate school, Lyle Jones at UNC, published a paper back in 1955 criticizing NHST, and then 45 years later, turned out it came out in the year that Tukey passed away, he and Tukey collaborated on another paper that said approximately the same thing. Bill Rosenboom also had this long lag of 30-some years between his first publication criticizing NHST and the resolution. And Bacon and Jack Cohen and Jim Steiger from our program here at Vanderbilt have all published papers. Lee Wilkinson and his colleagues, that 1999 is the reference to the ultimate paper that resolved the issue for the APA. And so what did Wilkinson and his group say? Cohen, the original chair of the task force, had published this paper saying that there's certain concerns with NHST that we have to account for. One is that all null hypotheses can be rejected if the sample size is large enough. So in a sense, NHST becomes the challenge of having enough money to buy enough data that we can reject the null hypothesis. So that doesn't sound quite right somehow. Of course, statistical significance does not in any sense imply practical significance. Maybe there is a real honest result of the Rodgers IQ improvement system. Maybe it is real and significant. But if it improved your child's IQ by 1/10 of an IQ point, and I'm charging $1 million for that, how many want to stand in line for that? It's significant, it's real, but it's not big enough to be meaningful. And many have suggested that NHST is in fact backward logic, that the probability of the data given the hypothesis is the reverse of what we want. What we really want is the probability of the hypothesis given the data. That's Bayesian statistics. That's why so many of us, I love Bayesian statistics, although I don't worship at the altar. You'll find people who are practicing converts who can't think any way other than through Bayesian methods. I grew up a frequentist. I think frequentist. I bring Bayesian machinery in, and it really helps me in all sorts of settings. So the Bayesian logic makes tons of sense. And finally, just a lot of folks have said NHST doesn't sound like a good way to run a science. My most fundamental statement about NHST is that it's a fairly impotent system where all I get to say is that the opposite of my theory doesn't seem to be wrong. Or the opposite of my theory is wrong. Did you hear me say anything about my theory? I just said things about the opposite of my theory, or the converse, or the obverse of my theory. Okay, so lousy way to run a science. So Wilkinson et al. Rendered their verdict. They were charged to actually stand up before the psychological community and say, so, Frank Schmidt, is he right? Should we simply disband NHST? And they said, no, that's crazy. They said it's crazy in the same sense it would be crazy for a whole union of carpenters who have been driving in screws with a hammer. So we're going to outlaw the hammer. That wasn't their analogy, but close. What they said was, no, let's sharpen the techniques and the tools. Let's teach those carpenters how to use a screwdriver. NHST should not be outlawed, but statistical practice should be revised substantially, they suggested. Effect sizes, confidence intervals, meta-analysis, graphical procedures, and so on should be emphasized. And now, for all the fascination of that, I have to transition to my own opinion. We didn't call them blogs back then, but I was on 25 listservs, and I read every single day for several years the opinions of the smartest people I knew about this issue. And I never contributed a word. And it's not because I'm just shy and a wallflower and don't ever want to go out there. The reason I didn't ever contribute anything is because I was thinking and preparing to write this talk. My position is that no revolution needed to occur. Frank Schmidt did not need to call for NHST to be outlawed because the really honest, important revolution had already occurred and was sitting there right in front of us. The quiet revolution to which I refer, and I'll call it the modeling revolution, that's not a perfect name for it, but it's not bad, it's at least descriptive. The modeling revolution is a shift from a statistical paradigm to a researcher's paradigm. Researchers should hear that sentence and say, wow, that sounds sort of cool. The real revolution, the modeling revolution, is a shift from computational formulas of the type that Fisher developed to conceptual formulas of the type that I'll show you in a few minutes that are very useful and effective. The question compared to what that Fisher had us start thinking about ultimately, in this new paradigm, becomes compared to other models that are reasonable competitors. Instead of compared to chance, instead of positing that chance effects are how the world works and either saying yes or no to those, in this case, we have actual competition between interesting, useful behavioral models. Sounds like the kind of thing researchers do and the way researchers think, and indeed it is. The focal point has shifted. The analytic approaches that reflect the modeling revolution weren't occurring in the late 1990s. They were being developed in the 60s, 70s, and 80s. They were already in place and already being used. Structural equation modeling is an example. Hazards modeling, log linear modeling, arithmetic moving average models, hierarchical linear models, multi-level models, and so on were models that had been developed according to a different epistemological system And it's like all these folks who had helped develop these models weren't even thinking carefully about what they'd done, in my humble opinion. So this is another palindrome. It's a palindrome that the parentheses are supposed to separate it out. I'm going to talk for a couple of seconds about the difference between behavior fit to design models and models designed to fit behavior. So in some cases, models are, like analysis of variance, are useful to transport across different domains. Regression analysis can be used in 1,000 different ways. Structural equation model can model this or model that or model that. On the other hand, I know a lot of cognitive modeling experts who built a Atkinson and Shiffrin memory model to model one exact process, this one right here. They're similar in how they function. They have data, they have mathematical structure, and they estimate parameters. But one set of models are designed to do all sorts of things. The other set of models is designed to do one very specific thing. So there's tension between these two approaches, using statistical procedures to build models of behavior versus building statistical models to fit behavioral processes. This is what we teach folks. This is where all of our pedagogy is. I'll bet hardly anybody in the room ever took a course. I know of 1 or 2 courses in the U.S. that are like this. Hardly anybody has ever taken a course, I'll bet, in how to build your own model. The courses you take are in how to use multi-level modeling or how to use structural equation modeling. Judea Pearl, writing about causal modeling, said, modern methods bespeak an alarming tendency among economists and social scientists to view a structural equation as an algebraic object void of causal content. Then he continues, SIM practitioners, structural equation modeling practitioners, have sought to gain respectability for SIM by keeping causal assumptions implicit, since statisticians, the arbiters of respectability, abhor assumptions that are not directly testable. And so let's go back to EMOSA models for a couple minutes and examine those and see how they fit into this framework. I have to admit, I'm going to quote myself with a little bit of embarrassment, but I can't improve on the words that I spent, hours and hours trying to write down if I just go extemporaneous. It won't be quite as well said as I said it in the original publication. This is in a developmental psychology article where we said linear equations seldom are developed as descriptive models, whereas systems of nonlinear dynamic equations, like EMOSA equations, typically do reflect a simplified form of the empirical processes they are trying to model. And even more expansively, I like this statement. I can't do much better than this. I think this is a good way to say it. These models are generated from processes that are more realistic than those for which linear models account. For example, no one believes that an adolescent deciding whether to engage in sexual intercourse for the first time explicitly evaluates their biological drive and weights it by a constant, adds that to a weighted measure of peer pressure and subtracts the weighted measure of religiosity, and then makes a decision about sexual behavior or anything else on the basis of that computation. No one really thinks that. Yet we understand that adolescents may approximately behave as though they're making this computation, and therefore the model is predictive, if not descriptive. On the other hand, our nonlinear dynamic models, our EMOSA models of adolescent sexuality, use mathematical equations derived by assuming that adolescents interact with other adolescents, pair up with opposite sex partners. That model reflected a simplification, a substantial simplification, but still a simplification of a social process that we presume to actually occur. And so that's an important distinction that emerges from this idea of just using models and plopping them down where they can be useful versus building a model that might actually do what you want it to do. So our EMOSA smoking and drinking models are interesting in all sorts of respects. These work the same way that sexuality models do, except that they're single-sex models. We don't need to posit opposite-sex partners coming in contact. They have the same types of filters and mixing adjustments and so on that I haven't really gone into in this talk. There's more focus on developmental stages. Theorists and empirical researchers who study smoking think about stages of smoking. And so here we have in the social contagion context the idea that non-smokers might with some possibility become triers, people who have ever smoked a cigarette for the first time. possibly through the influence of other adolescents. And then triers might become addicted smokers, again, through some social contagion process. And ultimately, smokers can go back and forth between being recovered and actual smokers. And not surprisingly, I'm not going to spend a lot of time dwelling on the equations, but there are equations that sit underneath this picture that look very much like the earlier equations. Now I need to introduce a new idea. I've been talking about social contagion so far, and if I walk up to Gary and I hand him a cigarette and I say, hey, try this, man, this is really cool, then I am engaging in a type of social contagion. On the other hand, suppose Gary is sitting in his living room watching TV. This really cool cowboy kind of guy, riding the range, comes up. He's smoking a cigarette, and he sort of growls and has a raspy voice. We know why. Has a raspy voice and looks like the kind of guy Gary would like to be. And then he's reading in a magazine, and he sees a picture of some peers who are smoking cigarettes, and he thinks, wow, they look like the kind of guys I'd like to be friends with. That's a process that we've referred to as diffusion as opposed to social contagion. I'm not sure I love that name. It's not my name. It's just what I inherited. So social diffusion of influence versus social contagion of influence is what we're talking about here. We can illustrate this. That's supposed to say Jack. And so Jack is a non-smoker. And Jack has all of these different processes, social, cultural influences impinging on him. And as they impinge on him, over time, eventually, he may become a trier. You see his color change as he becomes a different status. But in addition, there also are many individuals in his environment, and some are smokers, some are recovered smokers, some are triers, some are non-smokers. And eventually, he's likely to make friends or come in contact with a trier who influences him through direct social contagion to become a trier. And then he eventually becomes a smoker through contact with some regular smoker. And so those are the two different illustrations, one of social contagion, one of social diffusion. Work by David Rowe and his team at Arizona in the 1990s showed that the onset of smoking is mostly about social contagion. That's important. That's been used by smoking cessation countries or processes around the country. Programs that have been developed to help adolescents be convinced not to smoke have capitalized on the idea that the onset of smoking is usually about social contagion, but the next step is different. The next step is closer to social diffusion in its etiology. And so in other words, kids start smoking because their friends encourage them to. They continue smoking because of the presence of a smoking culture in their families, on TV, or in magazines. These two processes are similar, but they have substantially different policy implications, and you can chase that on out in your own thinking. It turns out that the two processes can be distinguished empirically. I discovered this by reading a very old 1950s article from the sociology literature where they talked about the S-shaped curve versus the negatively accelerated exponential curve. These two curves differentially account for the two types of equations that go into diffusion versus contagion. And so an S-shaped curve is characteristic of a kind of process that has contagion, direct one-to-one influence underlying it. On the other hand, the negatively accelerated curve is characteristic of the kind of equation that you write when you're trying to account for social diffusion. And so all of a sudden we had a neat new laboratory, and we applied this to a number of data sets. So here's a set of prevalence curves that were obtained from a nationally representative sample of adolescents in 1980. These are U.S. male sexuality prevalences for blacks and Hispanics and whites. You don't have to look very long to see the S-shaped structure. And so the work by Burt and others, to which I referred, would suggest that there's some kind of social contagion process, or at least the equations that generate these curves come from the kind of equations that have social contagion involved. Here's another one that we collected. In 2003, we did a survey of several hundred college students at OU, and we asked them about their first smoking and their first drinking experience. Then we backed up in time to when they said those occurred, and we built prevalence curves, and so this is what they looked like. The top curve is the alcohol curve. The bottom curve is the cigarette curve. S-shaped? You bet. As opposed to the negatively accelerated exponential function that we saw associated with diffusion. And furthermore, and this was a validity study, we asked them to write little diary entries describing their first smoking and their first drinking experience. And in these data, where the curves speak up and say, hey, social contagion may be going on here, many, many, many of those adolescents, these are college students writing about earlier experiences, said things like this. Well, I was with a group of guys, and Johnny passed me a cig and said, hey, try this. Or another one said, my best friend and I went to the movies, and she had a cigarette in her purse, and when we got out of the movie, she said, hey, you want to go smoke this cigarette? And I said, sure. It's hard to think of more socially contagious behavior than those descriptions. And so we were convinced that indeed there were social contagion processes underlying most of the transitions for these adolescents. Raoul Hoffman again, our Nobel Prize winning chemist, said that uncomplicated models play a special role in the acceptance and popularity of theories. Among other theorists, the models become modules in a theoretical erector set, shuttled into any problem as a first, not a last recourse. And actually for Hoffman, these uncomplicated models are defined as previously specified models with analytic solutions like regression or ANOVA or structural equation modeling. That's the uncomplicated models. In his more mature field, I think we'd all argue that physics and astronomy and chemistry have been around long enough that they're a rather more mature science than education and psychology and sociology. In his more mature field, he viewed those as important, but they're the starting point for the whole process. And so following, I like this suggestion. Hoffman said that good theories become portable and stimulate experimentation and replication, and I quote, what excitement there is, he wrote, in person A advancing a view of how things work, which is tested by B, used by C, who tests the limits of the theory, which leads to D, not C, finding that relevant agent, whereupon a horde of graduate students of E or F are put into making slight modifications. And so I think that's a nice description of how we should be engaging in both our science and our pedagogy and our training. Models simplified as reality, or perhaps we're talking about reality simplified as models. A model is a very simple thing. It only has two features. The first is it matches the reality that it's trying to match. And the second is it's simpler than that reality. So think of the plastic model of the airplane. Matches the reality, but it's quite a bit simpler. Think of the Model T. The Model T is a representative car. It's not all cars, but it's supposed to be a model for all cars. It's supposed to represent them. It's simpler than all cars, but it's matching that reality. Pearl again says a model is an idealized representation of reality that highlights some aspects and ignores others. Duncan Luce said that mathematics become relevant to science when we uncover structure in what we are studying. And so let's go back a little bit to our review of the F-test. You were hoping to get through this without any equations at all, and I'm going to come close, but I'm going to have just a couple. So that is the famous F-test. Fisher did not name it after himself. He was too busy doing science to worry about that kind of thing, but one of his students did. And so it's called the F-test after Fisher, and we know that it's the ratio of two estimates of variance, one of which is sensitive to treatment effects and the other of which isn't. Those are both unbiased estimates. If the null hypothesis is true, they're estimating exactly the same. Oh, I listen to myself and I say, I like this stuff. I really like this stuff. I've said that so many times, but I'm not sure it really gets through to researchers. How about if we back up and reformulate this? It turns out that this equation, filled with sums of squares and variance components and so on, has an exact algebraic transformation that looks like this. Not much better yet, but let me interpret this for you. This is not sort of the same thing, folks. This is the same F statistic. This is derivable from this. These are exactly the same things. And in this particular equation, what it says is that my model that is bigger, the full model, and my model that is smaller, the reduced model, each have an R-square statistic that measures how good they are. And the difference between the goodness of those two models, the goodness of fit, is captured by that R-squared difference. You hand me one model, you hand me your competitor model, We'll estimate R squared using standard old regression ANOVA machinery and take the difference between those, and that says how much the bigger model improves in fit compared to the smaller model. Okay? Furthermore, tell me about how complex the models are. Take the difference in the degrees of freedom associated with the reduced and the full model, and now we're trading off. The way you trade things off mathematically is you put them in ratio to one another. So we're trading off the fit against the parsimony, and that's a scaling factor that we don't worry very much about. So it turns out that the F-test is not only the ratio of two variances, it also is a statistic that tells us how to compare one model to another model. Notice I never said anything about the null model. These are dynamic, active, interesting models. The null model has disappeared here. The null model, I guess, in practice is really the simpler of the two models. But it's an interesting model. It's not just chance. It's a real model that we can compare to the full model, and we can say, is the increase in R squared that we get by going to the full model worth the loss of complexity that we get by going to the full model? Potentially, if you embrace that and wrap your thinking around that, I think researchers typically like this a whole lot better than they like this. James, you have a feeling you've been around this block a few times before. So now let me talk for a couple minutes about putting the heart before the course. Many people have written the same kinds of things that I'm trying to sell you folks today. Shadish, Cook, and Campbell have been writing about quasi-experimentation. Campbell started back in the 60s and said many things that are similar to my comments today. Judd and McClellan wrote a wonderful book in '89 that was so far ahead of its time that nobody used it. I only know one person, my colleague at Oklahoma, Robert Terry, had the nerve to use Judd and McClellan in undergraduate stat classes, and he could make it work, but even I didn't have the nerve to use it. They've released a new version of it, and it's marvelous. It really is all about modern statistics. Estes in 1990, Maxwell and Delaney in 1990. McGrath in 2011 has a brand new book. Jackard and Jacoby are all talking about the same kinds of things I'm talking about. This isn't my ballet in a bathtub. It's not my sole story that I'm trying to sell. A lot of people embrace this. A lot of people who are smarter and have been at this for a long time, doing more of it than I have, are on that list. By the way, Scott Maxwell is a close friend of mine. His daughter just graduated from Vanderbilt about 4 or 5 years ago. Just thought I'd toss that in. So the philosophical changes implied by this transition move the null hypothesis into the background. They shift from testing the null to building and evaluating the researcher's model. Leads us to stop teaching that small p-values are good and big p-values are bad, because sometimes it turns out big p-values are good and small p-values are bad. And how do we know which is which? We think. We use logic. We use our researcher's lens to try and understand how we want the p-values to behave. Pragmatic changes. Well, we need to start teaching explicitly how to build and evaluate and compare models to one another. Several of you in this room have sat through my courses where I talk a whole lot about the importance of comparing models one to the other. Scott Maxwell's textbook has in its subtitle a model comparison approach. That's 1990 when Scott Maxwell first wrote that. We need to develop flexibility in how to measure complexity of a model, not just through degrees of freedom, but also through all sorts of other very sophisticated approaches that people like N.J. Myung at Ohio State have been working on. We need to revise our thinking about power, about how to construct power tables and how to measure power. Bud McCallum and Michael Brown have done a whole lot of work on power and structural equation settings that reverses this concept. The recommendations of the APA task force is a very good set of recommendations. Jim Steiger in Psychological Methods about 10 years ago published an article that encouraged focusing on effect sizes and their confidence intervals, and that's a very nice article. So the threads running through the text, we need to start focusing on the models of interest. We need to change the Fisherian concept of degrees of freedom. More on that in just a second. And finally, we need to soften our statistical and methodological practice. And so there's a picture of the American Psychologist article that eventually did come out in 2010 with the title, The Epistemology of Mathematical and Statistical Modeling, suggesting not that we eliminate NHST, but that we use it as we always have, as part of the means toward the ends, but not the ends in itself. And so the word epistemology is all about how we understand the world. And my argument is that we shouldn't understand it through NHST. We should understand it through modeling, which uses NHST as a part of its machinery. So in no sense am I proposing to get rid of NHST. I don't think we should, any more than we would propose to a bunch of carpenters. You've got to trash the hammers because a couple of you have been misusing them. NHST is really, really good to do what it is really, really designed to do. Well, a year or two after that, I was invited to give an invited address at the Oklahoma Network for the Teaching of Psychology. And I wrote an address that's similar to this one on degrees of freedom, about how degrees of freedom work and why they work and how they should work. Fisher invented the name degrees of freedom. It's perhaps therefore no surprise to you that that name all by itself is so incredibly intimidating. I've been teaching them for my whole career, and I've hardly ever taught them and felt good about teaching them. Degrees of freedom. Degrees of freedom. You want to know what they really are? It's the dimensionality of a multidimensional constrained data space. You got it? Thank you very much. You can refer back to that statement a long time from now. If you remember it past about 30 seconds from now. There are other ways to define degrees of freedom. I would like to change the name of degrees of freedom to statistical money. Degrees of freedom are literally statistical capital. And if somebody besides Fisher had invented the concept of degrees of freedom, we'd be calling them something like that, statistical dollars or whatever. So I'm not going to go deeply into this, but this is a continuation of this thinking about how to soften the teaching and the practice of statistics in the direction of the researcher. And so now part 3 is actually my conclusion. Turns out that science has been down this road before. Everyone knows, I think, the story associated with Galileo about how he duked it out with the Catholic Church and they made him recant, and as he was recanting that his position was that the earth was not at the center of the universe, but rather that the sun seemed to be at the center of a system that the earth revolved around. Catholic Church viewed that as heresy, forced him to recant, and as he did so, he whispered into his beard, "Yes, but it does revolve." And so we know about Galileo. You may remember Kepler. Everyone knows about Sir Isaac Newton and the apple. He's the inventor of developer, discoverer of gravity and so on. During the 16th and 17th centuries, all of the scientific attention in the world was focusing on this question: how is the universe structured? And they didn't know. They didn't even know for sure if the earth was round, although pretty good idea that it was by this time. So there are pictures of these two important scientists, Galileo and Sir Isaac Newton on the right-hand side. And now let me tell you a little bit about the follow-up to my American Psychologist article, which follow-up is all about Galileo and Newton. So my friend Joel Levin and someone I've never met before, Daniel Robinson, published a fairly scathing critique of my American Psychologist article. They didn't publish it in American Psychologist. They tried, and American Psychologist turned it down. So they sent it to a statistical journal who agreed to publish it, and then they sent me an email and said, "You want to write a rejoinder?" And I said, "Oh, yeah, sure." And so this was a fairly scathing criticism of my paper because these are hardcore adherents of NHST. And they felt like I'd stepped all over their toes. They actually felt I was fundamentally wrong in all sorts of ways, and we could get into the details. He said, he said, he said, he said. But on the right-hand side is my response to their rejoinder, which is titled Statistical and Mathematical Modeling versus NHST, question mark. There's no competition. I've had friends ask me, did I mean the pun built into that? Of course I did. There's no competition. And so that reflects the fact that we sort of duked it out in this journal. In my conclusion of that article, I said, consider an analogy from the history of science. And I talk about a book by Davis Sobel on Galileo's daughter, and a book by James Glick, the marvelous science writer. In fact, these are two of the best science writers we have. Glick's book was a biography of Newton. And so reading these sort of together had already brought some ideas forward in my mind that I want to propose to you folks, and I'd invite your criticism and your collaboration on these ideas. But the important thing is that in the mid-1500s, Copernicus stepped forward before the world and said, guess what, folks? It's not that the Earth is at the center and the planets revolve around the Earth on epicycles on epicycles on epicycles. You remember this business? Clearly, circles didn't work, but circles on circles on circles on circles did. Sometimes it took 15 or 20 to actually fit the data. Copernicus said, I have a simpler version. It was only better because it was simpler. It didn't fit the data any better, but it was simpler. His version was, let's put the sun at the center. Well, not quite. Put the sun at one of the foci and let these be ellipses as the planets revolve around the sun. And everyone said, oh, you're nuts. No way to possibly grab a hold of that. And Galileo, at about the same time, a little bit after that, was a gift to Copernicus, invented the telescope. And as he invented the telescope and started looking at the sun and started looking at Jupiter, he ran all of these significance tests of the null hypothesis that the Earth was at the center of the universe. And the null hypothesis that had to do with the moons of Jupiter rejected the null in favor of the alternative that something else was at the center. And the null hypothesis associated with the way the sunspots moved and danced across the sun, that the Earth was at the center of the universe, was rejected in favor of some alternative. And the null hypothesis that the tides behave according to the way they would behave if the Earth were at the center of the universe was simply rejected. It's safe to say that Galileo believed in Copernicus, but it's also safe to say that he was not especially biased in that direction. I think he would have been quite willing to find otherwise if the data had spoken loudly, but the data didn't. The data said, we can reject the null hypothesis through all of these individual significance tests that were run through use of his telescope. And so that's a list of some of the things that I talked about, and I said each might be viewed as a separate astronomical significance test of the null hypothesis that the Earth was at the center. All of his observations lent credence to the unpopular sun-centered universe of Nicholas Copernicus. Kepler came along, and in the early 1600s, he actually took Galileo's stimulus and started writing down some equations, some laws. And then, ultimately, Sir Isaac Newton, who interestingly was born in the year that Galileo died, so there's a nice time link between them. When he was 23 years old, just like T.S. Eliot, he did three things. He invented calculus, because he needed it. He showed how a prism could be used to break down the light into the spectrum. He showed that light is composed of many different colors. And the third thing he did in his spare time was to write the equations for the universal law of gravitation. 23 years old. The universal law of gravitation was an equation, a system, a model. It could not have happened without the individual significance tests that Galileo had been through. And so I'm proposing to you folks today that we're in the same type of development within social and behavioral science that they were back then. We've been strongly embedded within an NHST significance testing context for a long time. And now at least some researchers, not all, not Levin and Robinson, that's okay, some researchers are transitioning out of that into a model building paradigm. And if you're ready for that, more power to you. Thank goodness for Sir Isaac Newton. As Alexander Pope said, let Newton be and all was light. Thank goodness he could build the models, but if he hadn't had the data and the information and the significance test provided by Galileo, he wouldn't have known enough to build those models. And so back to those pictures, and you can see at the bottom we have a type of astronomical NHST paradigm that Galileo was embedded within. And ultimately then Newton and Kepler both broke out of that paradigm and developed what we all know to be one of the great, great scientific contributions in history, the universal law of gravitation. So we've now come full circle. One of my students said, you ought to refer to Newton's third law at this point. For every action, there's an equal and opposite reaction, a constraint of nature. And I think he had in mind the reaction of the Catholic Church to Galileo and about how things go full cycle. T.S. Eliot's writing is filled with poetic constraints. Art is filled with visual and spatial constraints. EMOSA models are filled with mathematical constraints. And so it's all about constrained language structures. It's all about building these systems that it turns out are much closer to one another than one might think in the context of constraints. And so my real conclusion is to tell a little bit of a story about what happened when I tried to publish my whole article and they wouldn't let me. NHST answers a certain kind of question, but it is not and should not be, in my opinion, an organizing system, an epistemological system. Mathematical modeling, statistical modeling subsume NHST. They include it as a special case, and they're more natural methods for use within a maturing science. And I believe modeling has epistemological status, whereas NHST doesn't. So I begin by talking about modeling as language and art, and that's where I'll also conclude, because when I tried to publish the ultimate version of my article, when I say ultimate, it went through 14 revisions, maybe 25, maybe 150. I had a very telling palindrome at the very end. And the palindrome was supposed to make the point that this whole talk has made, that we have constrained language structures and mathematical models fit right in to that context. Well, the editor was convinced by a reviewer that my palindrome was superfluous. And at the very end of the whole process, after I'd been through all these 14 revisions, the editor finally said, "Rodgers, take out the palindrome and we'll publish your paper." And I wrote back and said, no thanks. I want you to publish my paper, but it's my paper. I get to decide what goes in it at a fundamental level. And the editor engaged in a little bit of turf expression and said, well, maybe, maybe not. But let me just let you know that if you want to publish your article, you've got to take the palindrome out. And so for 2 days, I was prepared to fall on my sword and take my article out. Remember, 5 years in the development, 5 years with a single journal. All these reviewers had helped me craft it into a better article and so on and so on. It was ready to go. And I thought the palindrome was the ultimate statement. So I took it out, and I still think it made a real contribution. So the editor made me take it out, but the editor cannot keep me from showing it to you folks. I'm putting it back in here, and I hope you'll appreciate that models are a way of communicating just like language structures. That was the point. I tried to convince the editor and the reviewer of the value of that. So the title of the palindrome of the conclusion to my article used to be Revolution Backward and Forward, Forward and Backward Revolution. And so here's a palindrome at the word level that says change in results, statistical results in revolution. Null hypotheses are gone again. Theories are simple and convincing summaries. Summaries, convincing and simple, are theories. Again, gone are hypotheses, null. Revolution in results, statistical results in change. And I would welcome questions, comments, critique. If Robinson and Levin are in the room, I'll be glad to engage in some verbal fisticuffs. That'd be fine too. We have time, I think, yeah, a little bit of time. We're close to out of time, but I'll be glad to stick around as long as you folks want to and talk about these issues.
Joe, if I could, just offer a question, because I've read the paper and I've read this twice, and one of the things that I've been trying to think about, and I would say, I hope you all agree with me that Joe has given us a treat that has much more lasting sustenance than the cookies in the back. But
pretty good cookies.
It's given me intellectual sustenance over the last year thinking about this in many ways. But one of the things that has occurred to me is trying to come to grips with the idea of a descriptive model, where you're looking at naturally occurring events and you're modeling them, you're simplifying them for purposes of the description and explanation of what goes on, and the kind of stylized way that we approach causality, with preferring, for very good reasons, randomized experiments. And then it strikes me that as I've thought about it, what you're arguing is not that we should move and not do randomized experiments, but in terms of how we think about things, if we don't have an adequate description of the processes going on, then our attempts to develop the interventions and manipulate are probably going to be we're going to get a lot fewer hits because we don't understand the process to begin with. And I just wonder if you would sort of give us some of your thoughts about how this, with our push toward causality, how those things fit together for you.
So, Gary and I have talked about this before, and I think others in the room will appreciate this statement. I think it's all about threats to validity. I think research is all about eliminating all the threats to the validity of our final conclusions that we can. So I've been talking about one set of threats, and those are statistical conclusion validity threats. Those are threats to the validity of the conclusions because we used an NHST paradigm when we should not have. It's not that NHST is bad, but it is bad when we use it where we shouldn't. Another threat to validity is where we have an assumption built into our statistical model that's inappropriate, and we don't admit it, we may not even recognize it, and we go forward, and it turns out that had we been able to see the book of the way the world works, see the behind-the-scenes processes, those assumptions would be laden with all sorts of challenges to our interpretation, threats to validity. So my talk today is not about methods, it's about statistical methods. Another equally important, maybe more important, critical feature of methods is the quality of the design. And I am not a passionate devotee that you have to have random assignment or we might as well go eat pizza. What I say is if you can use random assignment, then you can eliminate all sorts of threats to validity that you can't otherwise. And so what a powerful tool it is. Is it the only tool we have? Nope. There are other ways to nail nails into a board than this 9-pound hammer. You know, there are other hammers, there probably are other techniques. My shoe might even work, not very well, but might work. So there are all sorts of ways to address threats to validity, and they emerge from design. They emerge from measurement. Measurement was my original, I was a psychometrician before I was really, before I ever saw Cook and Campbell or Shadish Cook and Campbell and started reading about design. Measurement is an area where there are all sorts of threats to validity. I didn't say a single thing today about measurement. I could. There are other critiques and comments about measurement that we could discuss. But today's talk was about statistical modeling. I think it's interesting that we teach 2 or 3 classes of statistical modeling to all graduate students. At best, they'll get 1 course in measurement. Sometimes they get a course in design. Seldom, in most of our science at least, do they get a course in sampling. So somehow statistics has sort of risen up and become, this is more support for the idea that NHST is a little bit too big for its britches, not through its fault, not because Fisher made it that way, but just because the field has sort of lifted it up and said it's so important to know how to. So there are whole courses in the ANOVA, and then the next course is in regression and correlation. I sometimes think, well, that's the way it should be in one system because our journals are filled with ANOVA and regression models that either sell the article or don't. Unfortunately, Gary, I think, in my opinion, that a lot of articles ought to either be sold or not on the basis of the quality of their design. And if someone didn't randomly assign and use a true experiment where they could have, then that's grounds for rejection in the same sense that if you use an ANOVA when you should have used a multi-level model, someone who's smart about reviewing that article is going to criticize it in that way. Threats to validity. We're trying to eliminate those in design, measurement, sampling, statistical analysis, and ultimately in the logic with which we bring to bear our thinking on trying to model the world. And so it's a little bit of a cheap answer, I think, to say I wasn't talking about that, I was talking about this, but that's, you know, the threats to statistical conclusion validity are all about what I'm talking about today. And if you want a better treatment than I could give or anybody else has ever given to design issues, let's look at Shadish, Cook, and Campbell as a good place to go for the moment. That's about 10 years old. Their revision is about 10 years old by now. With good luck, maybe we'll get another one in a few years. So,
Will says no, but
yeah, yeah.
We've got time for perhaps one more question.
Well, it's late. It's 4:30.
4:30, so we should
Let's call it
probably
quits.
adjourn so we can now figure out how to put these great ideas that Joe's given us into practice. So let's thank Joe for the presentation.
Thank you. My pleasure.